requirements, we never connect that anywhere in the external circuit. But all op-amps have some problems due to the mismatching of the two stages, which in the differential amplifier stage, I've told you that the two sections should be exactly identical, but that won't be exactly identical. There will be small differences in the VBE values, and there will be small differences in the IB and IC and IE current values. That will produce some DC input voltages. Even if you don't apply a signal, there will be some small input voltages available at the inverting input pin number 2 and non-inverting input pin number 3 with respect to ground. See, the pin number 2 and pin number 3 are actually the bases of two transistors. The inverting input and the non-inverting input we have shown in the previous circuit that in the differential amplifier, the basis of two transistors. So inside this, we have two transistors, and pin number 2 is the inverting input. You know how we say one is inverting and the other is non-inverting? It depends upon from which point we derive the output. So that's how we say one is inverting and the other is non-inverting. That will be 2, 1. Then offset nullify means between pin number 1 and 5, you can connect a 10K pot meter, and you can connect your VCC to the wiper, and you can move the wiper in such a way that you measure the output voltage to be 0 in the absence of any input voltages. Something like this. What you do is this is your op-amp. Pin number 2 and pin number 3, which are this. You connect this to ground, connect this to ground. This is pin number 7 where we connect, say, plus 12 volt, plus VCC. Pin number 4, it's shown there, where we connect minus 12 volt. And this pin number 6 where you take the output. Now, you rig up this in the lab. Just connect your dual supply. That will provide the biasing. Although there is no inputs here, the differential inputs are 0. As per the connection, if you measure the output, you will see that the output is either at a positive DC voltage level or a negative DC voltage level. You can just check that in the lab in the next session. Even without a direct input, there will be an output. This is due to what we call the input offset voltage, VIO. There are many reasons for an input offset voltage, input offset or input error. There are basically two reasons. One is the change in the VBE value of the two transistors, which is used to design the emitter-coupled differential amplifier first stage inside the op-amp. They won't be exactly equal. The VBE value of one will be, say, 700 millivolt, which is your 0.7 volt, whereas the VBE value of the other will be maybe at 701 millivolt. So there is always a difference in VBE value which will come across these two bases. If you measure across these two bases, you will see 1 millivolt with this plus or this and this minus or the other way around. This is what you call the input offset voltage. Due to difference in the beta value, IC value will be different. Therefore, IB value also will be different. So IB1 will be different from IB2. These are all bias currents, DC currents. Now, if you rig up this, the current flowing through this, of course, it is of the order of few tens of nanoamperes, but this will be, say, 60 nanoampere, whereas this is 80 nanoampere. So there is also a small change in the input bias currents. So due to the change in this input bias currents, that will also, in effect, introduce a small differential input voltage here, because of the difference in this. So these all will get amplified, and you will get an output here. You know, for 741 op-amp, if you are operating it without a loop, what you call the closed loop, without that, if you are operating it in open loop, like this, this is going to give you a voltage gain of the order of several thousands. Several thousands. In the data sheet of 741C, you can see the differential gain or the open loop gain is of the order of 100,000 to 200,000. Although the typical value is rated at 100,000, it may range across 741Cs, it may range from 100,000 to 200,000. Which means that when you give a differential input VIO, or when differential input 1 microvolt is available here, as per this, the output has to be, say, 100,000 microvolt. 100,000 microvolt is 100 millivolt. 100 millivolt is, of course, 0.1 volt. So even if there is nothing here, there will be 0.1 volt. Normally, the VIO value won't be of the order of microvolt for 741. In the data sheet, it is shown that for 741, the VIO value is typically 2 millivolt. If one is 700, the other may be 702. So due to the difference at bias, there will be 2 millivolt already here. 2 millivolt into 100,000 is going to give you 200,000 millivolt, which is going to be theoretically 200 volt. 200,000 millivolt is going to be 200 volt. That means this diode will be saturated positively at plus V saturation. Of course, the output won't raise to that value because of the, you know why? Because of an amplifier, the output will never raise above plus VCC or minus V by design. So maximum will be plus V saturation. If the polarity here is just reversed, it will go to minus V saturation. Actually, the plus V saturation and minus V saturation, which we normally encounter in the open loop, is very close to VCC and VEE by design. If VCC is plus 12 volt, normally you can always conventionally take plus V saturation to be 1 volt or 1.5 volt below this. Again, to get exact values, you have to check that up in the lab. Whenever you use an op-amp, you know it's in the form of an IC. It's one of the easiest but not that exhaustive way of checking whether your op-amp is working properly is doing this connection. You connect pin number 3 non-inverting input directly to the ground. It can be other also. And you connect pin number 2 to your signal generator, which is available in all labs. You apply a sine wave of 1 kilohertz frequency. Provide the dual supply. Give this output to CRO. You will get a square wave in the output. You provide a sine wave. It need not be sine wave. It can be a triangular wave. It can be sawtooth wave. If you give any periodic waveform here, you will end up by getting a square wave in the output. Now check for these levels. This should be at plus V saturation. This should be at minus V saturation. For example, if you are using 12 volt, your plus V saturation is going to be leveled somewhere at 11 volt. It need not be exactly 11 volt. It may be 10.5 volt, depends on the individual op-amp. You can actually check that in the lab. And this will be at minus 11 volt. The peak of this square wave will be 22 volt. So in order to check whether your op-amp is almost okay, this is not an exhaustive test, but it's not an ideal test. But what you do is you just connect a signal here or here, keeping the other grounded, check whether you are getting a square wave of this amplitude. Frequency, of course, will be 1 kilohertz as a signal. This configuration is normally called ZCD configuration, zero crossing detector. Just configure your op-amp as a ZCD, give an input signal, check the output in the CRO. If you are getting something like this, you can be rather sure that your op-amp is okay for circuit applications. If you are getting something like this, the output amplitudes attenuated, that means that there is something inside that is drawing more current than actually warranted by the exact design. Better don't use it. So that circuit we are going to wind up after discussing that circuit. That's the op-amp inverting amplifier. We see that if it is in the open loop, the gain is going to be too high even for a very small signal. The output is going either to the plus V saturation or to the minus V saturation. So for any practical application as an amplifier, voltage amplifier, we have to bring the gain of this circuit down. You know, always the gain of an amplifier can be brought down by applying a negative feedback. We have applied a negative feedback. The output is sampled by the resistors R1 and RF and R. And portion across R is going to come between the inverting input and ground. And from the references you can see this. See, here the signal is applied to the inverting input. So when suppose the signal is an AC signal, when it goes positive, the output will go negative. That is why we call this as inverting input. There will be a 180-degree phase difference. And that will come back here. So whenever the input applied to the inverting input goes up, the feedback voltage, instantaneous voltage go down. That is direct opposition. So that way you can effect a negative feedback. Once there is a negative feedback, there will be a smaller output voltage for the same input voltage, or the gain of the amplifier will fall. The type of the negative feedback applied here is voltage shunt feedback. Voltage shunt feedback. In the transistor circuits we have discussed in the morning session, we know that the type of the voltage feedback, negative feedback, was current series negative feedback. This is voltage shunt feedback. In voltage shunt feedback, the input resistance will decrease and the output resistance also will decrease. In voltage shunt negative feedback, RIF, input impedance with feedback, is going to be smaller than input impedance without feedback. Output impedance with feedback, ROF, is also going to be smaller than output impedance. Of course, this is good. For an amplifier, a lower output impedance is good, but this is not good. This has some loading problems because the input impedance, due to that feedback, the input impedance actually falls down. In the open loop, the impedance between the two bases is the input impedance. For 741, Ri is approximately 1 mega ohm. PKL value is 1 mega ohm. It may go up to 2 mega ohm. Whereas, if you rig up that circuit, if you rig up a circuit like this, the input impedance affected for this source is just going to be 1K. It was originally a few mega ohms. If this feedback was not there, in the open loop, it was very high, of the order of several hundreds of kilo ohms or mega ohms. Once you make this connection, we implement voltage shunt feedback. Immediately, the input impedance will fall down to just whatever resistance you have connected here. If it is 1K, it will be just 1K. So that is going to produce some loading problems here. Okay. Now we can show by one or two steps that the gain of the circuit with feedback is minus RF over R. This is the gain of the circuit. So the simplicity and the significance of an amplifier like this is that the gain of the circuit can be very easily adjusted. By adjusting two resistive values, you can make the gain less than 1, greater than 1, make it 10, make it 100, make it 1000. This minus sign, of course, is because it is an inverting amplifier. Output and input will be out of phase. Now the design is simple. What you do is, now you can see I have designed for RF equal to 3.3K, R equal to 1K means the gain you are going to obtain is minus 3.3. That means if you give an input signal volt amplitude, in the output you are going to get an inverted signal of 3.3 volt amplitude. If you apply a signal of, instead of 1 volt, if you apply a signal of amplitude 4 volt, you are not going to, for the same connection, you are not going to get something 4 into 3.3, because 4 into 3.3 is going to be above your plus V saturation or below the saturation levels. So the output is going to be inverted, but there will be this saturation level. The output will be like this. Okay, that's all I think. So what you have to do, what you have to ask the students to do is to rig up the circuit and do the frequency response. Now one other thing, the frequency response will be like this. The frequency response will be like this. It won't be like this. You know why. The frequency response for any op-amp circuits will start from this point, because you know, by design inside a op-amp, there are no capacitor or inductive elements. That means it is able to amplify even DC signals. We can say the frequency of a DC signal is 0. If you apply, instead of an AC, if you apply a DC signal, it will provide the same gain, same amplification. So you'll get good gain, and after that, it will actually traverse the path of a typical low-pass filter. It will be something like a low-pass filter. This is the corner frequency. Now we have expressions for corner frequencies. Now the best book to get good ideas about, I think, op-amps and related circuits is your, what's that book? Op-amps and linear, the title is Op-amps and Linear Integrated Circuit by Ramakant A. Gaikwad. Got everything? Got every derivations as appendix? If you know the Laplace transform, the S domain, you can transform that into the S domain, and very, very easily you can derive the formulations that we are going to use in your next sessions for almost all circuits. Very simple job. That's a very good book to refer for all your op-amp and op-amp related 555, op-amp and other voltage regulator. Many circuits are dealt on which an op-amp is based. This is a very simple circuit where we have a closed loop op-amp which will provide voltage gain for your input. Since the input is connected to the inverting terminal, the output will be 180 degree out of phase with the input. That's why we call it an inverting amplifier. And in order to design the gain, it's very simple. Since it employs a voltage shunt feedback through the feedback resistor RF and the ground, the gain is given by a very simple relation. Although that is not the exact relation, it's an ideal relation, but that is always okay. Minus RF over R will give you the voltage gain. So it is very easy to adjust the gain according to our requirement. We can make the gain less than 1, or you can go to any value of the gain, depends on your requirement. It can be 10, it can be 100, it can be 200, so on and so forth, by adjusting RF and R. Here, as per the values given, 3.3K for RF and 1K for R, you see that the gain is minus 3.3, which means that if you apply a signal of amplitude 1 volt, you are going to get an inverted signal at the output whose amplitude will be 3.3 volt. Now, once you rig up the circuit, you have to study the frequency response and see whether it is performing the way it is doing. It's a very simple experiment for the students. There's nothing more to add on this as per our syllabi requirement. You can see there's just one difference in the circuit from the previous one. The signal is connected to the non-inverting input instead of the inverting input, so that the output will be driven in the same phase as the input. Output and input will be in the same phase. That's why we call this a non-inverting closed loop op-amp. Here, the gain is given by the formulation. Again, it is not the exact expression for the gain. You can derive it from the first principles of feedback. And incidentally, this circuit is employing voltage series feedback, which is one of the very best negative feedback, because output impedance will be very small and the input impedance will be too large. Especially for an op-amp, if you apply a negative feedback in the non-inverting mode, as shown there, that's the voltage series negative feedback, the input impedance will be enhanced to a large extent. You know, I've told you in the last class that the open loop input impedance of an op-amp is of the order of several hundreds of kilo ohms. For example, in the case of 741C, which we normally employ in our labs, it's around 2 mega ohm. 2 mega ohm is the rated input impedance, open loop input impedance of 741. So if you do a connection like this, the input impedance will be enhanced too much. The input impedance will be as large as several hundreds of mega ohms. So it will provide you practically infinite input impedance. That's why we say this is one of the best voltage amplifier. So that there will be practically zero loading effect for any signal applied at the input because of the very high input impedance. And the output impedance also will be too small, of the order of a few ohms at the most. If you measure the output impedance, you will see that it is around 10 ohms or less than 10 ohms for a circuit like this. Now the voltage gain is given by, again, a simple relation, 1 plus RF over R. For the non-inverting, it was minus RF by R. The negative sign, of course, suggests that output and input are out of phase. But here, since output and input are in phase, we have 1 plus RF over R, which means, again, that the gain of the circuit cannot be less than 1. The minimum gain that you can obtain using a non-inverting configuration like this is minimum 1. Normally, it is more than 1. Now, whatever value you require can be adjusted by using the resistor values RF and R. Remember, this employs voltage series negative feedback, which is one of the best technique, negative feedback, as far as the advantages of a negative feedback is concerned. This will provide very large output impedance, very small input impedance, large bandwidth, and the gain can be adjusted according to our requirements. So this, again, you can rig up and see whether you are obtaining the gain which you have designed for different inputs. And later on, you can also do a frequency response observation. So that's all you have to do on this. Now, this is actually a combination of two slides we have already discussed. Now, rushing up a little because of two reasons. One, these are all very simple. Of course, there won't be any problem for you, no problems while you do it in the practical lab. So that's why I'm rushing up. Now, this is actually the op-amp difference amplifier. As the name suggests, this will amplify the difference of the two inputs. The two inputs are shown as V1 and V2. V1 is connected through a resistor R to the inverting, and V2 is connected through another resistor R1 to the. Here, the expression here, minus RF by R, is valid only if this is equal to this and this is equal to that. For the given circuit, the expression given for the voltage gain, I've given the voltage gain equal to minus RF over R. AF equal to, AF is the voltage gain with feedback. I've shown it as minus RF over R, but that would be valid only if R1 equal to R and R2 equal to RF. The values are shown the same. R2 is equal to 3.3K, RF equal to 3.3K. Again, R1 and R are shown to be equal to 1K. Only if these resistors match in values, then you will be able to analytically show that the formulation for the voltage gain in the output is minus RF by R. This voltage gain is for the differential input V1 minus V2. So you can apply two inputs at the same time, or you can apply just one input. Both inputs may be DC, both inputs may be AC, or one input can be AC and another input can be DC, and you can see that the output is always conforming to the relation minus RF by R. V1 minus V2 into minus RF by R will be the output voltage VO. Now we'll just use the board for that. See, we are applying two signals, one V1, the other is V2. Then the difference of the two, VD, is V1 or V1 minus V2. Of course, it can be V2 minus V1. If difference is V1 minus V2, then the output VO is given as the differential gain, which is represented there as a feedback gain AF, into the differential input VD. This will be the output that you obtain in that setup. And this VD is this, and AF, which is the differential gain of that circuit, is minus RF over R. Now, we have RF equal to 3.3K, R equal to 1K. R1 has to be equal to 1K, R2 has to be equal to 3.3K. If R1 and R2 are different from R and RF respectively, you won't be able to represent the output voltage or the gain by a simple relation like this. This holds good. Of course, this can be can be derived in any standard book. In that Gaekwad book, it is derived. But of course, after the exact relation, in the exact relation, if you apply the condition that R of equal to R of equal to R2 and R equal to R1, you will come to this relation. Some of the terms from the initial derived expression will cancel off, and we'll arrive at a very simple relation, minus R of over R. So this will give you the output voltage in terms of the input voltage. Now, let us consider one case where we keep all the resistors equal. Suppose we connect R of R, R1, R2 with the same value of resistors. Then you see that R of over R will be equal to minus 1, because all resistors being equal. Say you are connecting 10K at all the branches, so the gain will be equal to minus 1. Then VD will be equal to, VO will be equal to minus 1 into VD, or VO will be equal to minus 1 into V1 minus V2, or VO will be equal to V2 minus V1. Then we say the difference amplifier is operating as a subtractor. The difference amplifier is operating as a subtractor in the sense that the output voltage is the difference of the two input voltages. So you can simply modify that circuit to act as a subtractor. The only thing you have to do is that you make all the resistors equal in values, so that the differential gain of the circuit becomes minus 1. So minus 1 into differential input will give you the difference of the two input exact. So it will work as a subtractor. 1K, that's what I've just explained. If you keep all those equal, then it will act as a subtractor. It's an amplifier. It's a difference amplifier with gain minus 1. So the output will be non-inverting input minus inverting input. I will give you an example. Say, in the circuit, suppose I keep V1 equal to 1 volt and V2 equal to, say, 2.5 volt. And I make all those resistors equal in value, say equal to 1K or 10K. Then the output you are going to get is V2 minus V1. The output will be exactly 1.5 volt. If on the other hand, you are keeping V1 to be, say, equal to 5 volt and V2 equal to 2.5 volt, then the output you are going to get is minus 2.5 volt. Remember, it is the difference V2 minus V1. V1 subtracted from V2 will be the output. So this will be the output, right? So always the output is given by this relation. It is output equal to AF into VD, where VD equal to V1 minus V2. Remember, as per that design, V1 is given to the inverting input, V2 the non-inverting input, and differential input is represented as V1 minus V2. Then VO equal to AF into VD, where AF equal to this. So if you keep all resistors equal, then this will come to minus 1, so it will work as a subtractor. Now you will also ask the students to test what happens if one of the input is DC and the other input is AC. Suppose you keep V1 to be at 1 volt DC. I just wanted you to let your students do this. Connect a DC source here and an AC source here, and what will be the output? I want them to do the output analysis. Now you can, of course, you can verify it on the CRO, but before verifying it on the CRO, you will ask your students to do it in paper and ask them to show the output waveform if one of the input is a DC and the other input is an AC. Right? What happens is this input, DC input, which is connected to the non-inverting, will be amplified. What will be the gain? It will be amplified so that the output is equal to that much positive DC. Now, So here we have two inputs. V1 is a sinusoidal waveform of amplitude 1 volt of some frequency. And V2 is a DC, a positive DC 1 volt. So I'm going to represent these two in this plot. This is the time axis and this is the voltage axis, and this is say 0. So this can be represented as a DC. This is a DC representation for V2. This is at a level 1 volt. And the AC is having a peak of 1 volt again. So I'll represent that here. This is at plus 1 volt. This will be at minus 1 volt, the negative peak. So this is your V1, this is your V2. Now, what will be the output? I will just represent the output here so that we'll be able to see why the output is the way it is. Now, for this 1 volt DC V2, this circuit will perform as a non-inverting amplifier. A non-inverting amplifier has a gain 1 plus RF over R, we discussed in the previous slide. So in this case, since the RF equal to R, this will be equal to 1 plus R by R equal to 2. So for any signal appearing at the non-inverting input with respect to ground, this circuit is going to provide a gain equal to 2. Now we have applied the signal 1 volt not here, but here. So when you apply 1 volt here, the potential here will be just 0.5 volt, which is easy to find because these two resistors are equal. If these two resistors were not equal, then you will have to do a potential division and see what will be the potential coming across R. For example, suppose this was equal to 1K and this was equal to 2K. Then if you apply 1 volt here, here you will get 2 by 3 volt. 2 by 3 volt across the 2K, 1 by 3 volt across the 1K. That will be the division. Since now in our case, both were at the same resistors, say equal to 1K, the input 1 volt will be equally divided across these two, so that at the non-inverting input and our ground, we will get 0.5 volt. So this 0.5 volt will be amplified 2 times. When 0.5 volt is amplified 2 times, the output will be 1 volt DC. So even if this signal is not there, even if this point was directly connected to the ground, even if your V1 was equal to 0, you are going to always find the output at 1 volt DC level. A 1 volt trace above the reference, that will be what we pictured on your CRO screen. Now we say that we are also applying this 1 volt. Now for this, it is being at the inverting input. You know the gain for the inverting V1 signal, which is being at the inverting input, is minus RF over R, which is equal to minus 1 in our case because these are equal. So when you apply a 1 volt signal here with positive cycle, negative cycle, what we get there is a 1 volt signal but inverted. So instead of this, in the output we'll get this. So I will call this VO1, the output corresponding to V1. And this is 1 volt DC in the output, which is our VO2 corresponding to V2. So these two will be together present in our output. So what will be the output? Now the output will be something like this. The reference is shifted to 1 volt and the output will be having a peak equal to 1 volt but inverted, and this is what you are going to find on the, this is your final output. So the effect of this is that the output will be inverted because the signal was given to the inverting input, and the reference level, which was originally at 0 for your signal, is now shifted up due to the DC. So output will be this. So you can test it for different signals, different values of amplitudes of signal. You can make an inversion here. You can just do this negative here and positive here. So in that case, what happens? This will just shift back here and the output will be this. The reference of the output, inverted output, will be at minus 1 volt. Okay. So that also can be verified. Nothing else there. You just verify for different inputs. If you give this without a potential This again you can do the same thing. If you are like this, then this will be amplified as much times whatever be the gain. Now that it's a case like this. Yeah, you are right. Suppose we have a situation where we directly connect a 1 volt or some other potential here, and this part of course is this. Here I have our AC signal, say VI or V1. So this 1 volt will be here as VO of this. We'll call this 2. So VO2 will be equal to V2 into 1 plus RF over R. RF and R will decide the gain. So VO2 will be this. It will be DC. It will be a positive DC. So the reference will be above. And for this, it is minus VO1 will be equal to minus V1 into RF over R. It will be an inverted waveform with an amplitude equal to V1 into RF by R. No, you can't use that equation. You can use this equation only if R equal to R1, RF equal to R2. But if it is some other, you can always do it like this. For any resistive values, you can perform exactly this. So whenever you have to analyze an op-amp circuit where it is fed with inputs more than one, it can be 2, it can be 3, it can be 5. It can be 2 inputs to the inverting and 3 inputs to non-inverting. In all such cases, there is just one method. Treat each input separately. That's the easiest way. Instead of taking all into your into analysis, you consider each one by one. Meaning, suppose I have V1 and V2 connected to the inverting input, V2 and V3 connected to the non-inverting input. You forget about V2, V3, V4. Consider only V1. When you say we forget about V2, V3, V4, we have to see that they are zero. They are zero that in the sense that that also is something that I think you should tell your students. Suppose we have a case like this. For simplicity, I keep these two equal. It need not be equal, say R1 and R2. Here I have a V1, here I have a V2. And here suppose it is like this, V3. Then I have 3 inputs here. Now what will be the total output in such a case? What you do is you treat each separately. You consider V1 alone. That means you connect this to the ground. You connect this also to the ground. This R and this R will become parallel. It will have a resultant equal to R by 2 between the non-inverting input and ground. Here R2 comes between the inverting input and ground. You know something, for an inverting amplifier, this inverting input is supposed to be at a virtual ground. Now I don't go into that, but anything, for analysis part, you just consider this to be at zero potential. That is because of the very high gain of the open loop gain of the amplifier as well as very high input impedance. Practically, you can always treat the inverting input of a closed loop inverting amplifier, inverting input of a closed loop inverting amplifier. It won't hold good for a non-inverting amplifier. For an inverting amplifier with a closed loop, you can always treat this point to be virtually at the ground potential. Therefore, even if you connect this R2 to the ground, this is not going to alter the gain equation or the gain value of a circuit. So you can find V1 alone. The gain for V1 is minus RF by R1. You can find VO1. Now you connect this to ground, treat only V2. For that we will get the gain equal to VO2 equal to V2 into minus RF by R2. Then you connect these to the ground and consider only V3. But for V3 it is not that easy because V3 is connected here. First what you have to do is you have to do that potential drops. You have to find the potential drop across this R because that effectively comes between the non-inverting input and ground. And for that, this will offer a gain equal to 1 plus RF by R. Again, there is another problem here. R has changed because V1 is at ground, V2 is at ground. This R1 and this R2 will be parallel between the inverting input and ground. So R1 parallel R2 will be the effective R. Therefore, the gain is minus Rf by R, where R is equal to R1 parallel R2. Then 1 plus Rf by R will give you the gain for anything here. So that way you can also find VO3. So once you know VO1, VO3, VO2, you just sum that up, what you call the superposition theorem, always we use in electrical circuits. So using or following the superposition theorem, the final output VO equal to VO1 plus VO2 plus VO3. So that is how we treat or analyze any such op-amp circuit with more than one input. When you consider V3 to be at ground, as she has pointed out, when you connect V3 to be at ground, this R actually comes parallel to this R. That means between the non-inverting input and ground, we are going to get a resistance equal to R parallel